Okay, so we're continuing on from yesterday with vectors and planes. And so today we're looking at basically leading into finding the distance from a point to a plane. So example 5 says, find the coordinates of the foot of the perpendicular from that particular point to the plane. So if I were to draw a plane sort of as a parallelogram in 3 dimensions. So here is the foot of the perpendicular. So basically there's a perpendicular, and we want to find, or we're told, another point outside of the plane, and we want to find the point on the plane that's perpendicular to that. Okay, so this is what we're trying to find here. Okay, so basically that we can form a line between those 2 points and then find the intersection of that line and the plane. Because really, this is, we can extend this out, so there's the line there, and the line keeps going, right? So what is the equation of that line? Okay, so we need a position, so that's 4, 5, 6. Okay, and we need a direction vector. Now, remember, we've learned that that's the Cartesian equation of the plane, and the coefficients of the x, y, and z will give you the normal to the plane. So the normal is 1 to -2. So the normal to the plane means it's perpendicular. So that's actually the direction vector of this line. It doesn't matter which direction. It can go in either way. So 1 to -2. Okay, so now we want to find the intersection of the line. Oh, okay. Line with the plane. And because the plane is in Cartesian form, we can substitute the parametric equations of the line into it. So actually, I'm going to see if I can move this down. And so that means x equals 4 plus t, y equals sorry, just a sec. Oh, this board, I tell you. Okay, that's easy enough. 5 plus 2t, and z equals 6 minus 2t. Okay, so then we can substitute into the plane. So for x, 4 plus t, plus 2 times y, 5 plus 2t, minus 2 times z, 6 minus 2t, equals 9. Right, and so then just solve that equation for t. And get rid of the brackets. So the t value that we get is the parameter that when we put it back into the equation for the line, it will give us that point of intersection of the line, which is the foot of the perpendicular. So t is 7/9, and then you can substitute it back in to get your x, y, and z coordinates. Okay, so common denominator 936 plus 7 is 43/9. 45 plus 14 is 59/9. And 54 minus 14 is 40. So therefore, the foot of the perpendicular is 43 ninths, 59 ninths, and 40 ninths. Okay, so what that's going to be helpful for is finding the distance from a point to a plane. It's one method of doing that, and that kind of leads into the next question. Okay, so question 6. So it says, find the perpendicular distance of the point 456 to the plane using 2 different methods. First method, use the coordinates of the foot of the perpendicular and point P from example 5. We take a look back at that diagram. So we're trying to find this distance here. Now we have this point and we have this. So you can just find that vector between them and find the magnitude. Okay? Or the distance between points, back to Math 10, right? We just did it in 2 dimensions in Math 10, but it's the same thing. It all stems from the Pythagorean theorem. So here, so I'm going to call that, I'll call it F for foot. So FP is going to be 456 minus 43 ninths, what was it, 59 ninths, and 40 ninths. So what is that going to be? Common denominators again, right? 36 minus 43 is 7 ninths. Sorry, negative 7 ninths. 45 minus 59 is negative 14 ninths. Register. And then 54 minus 40 is 14 ninths. Okay, so we're finding the magnitude of that vector. So negative 7 ninths squared plus negative 14 ninths squared plus 14 ninths squared. Okay, so you can use your calculator if you want to enter those in. Convert it back to a fraction. Obviously, they all have the same common denominator. So you can probably, your math is 35. Right, without a calculator. So there's the root of 441 over 81. 81 square root is 9, and 441 the square root is 21. Which actually simplifies. So you could have simplified that fraction, but this works out to 7 over 3. Okay, so that's the distance from the foot of the perpendicular to point P, using our work from example 5. Then the second method says using the dot product and the definition of cosine. So this will take a little bit of an explanation, but then this may end up being an easier method rather than going through the intersection, finding what might be a t-value that's a fraction and that kind of thing. So let's draw the plane again here. Okay, and so we have, I'm calling that F, we have point P up here. Okay, so we want to find this distance. Well, if we chose another point on our plane, I'm going to call it T, okay, but we could form a vector, ET, right? And we could, if we do that, we will have an angle in between those, theta, and that is going to be, right, this is going to be, no matter where that point is, it's going to form a 90-degree triangle, okay, because F and T are on the plane. So 90-degree triangle, cosine is adjacent over hypotenuse. So we can then end up finding that side. Saying that, we need to know what theta is. How are we going to get that? Because we don't know this vector yet. Okay, we have to pretend that we didn't figure out what f is. So that's where the dot product comes in to help us. Okay, so choose a point on the plane, and I'm going to call it T. Choose an easy point. So if you look back at the equation of that plane, put in some zeros, right? So if I let y and z be 0, x is 9. So that's a really easy point to deal with. Okay, so I'm going to reform this triangle just itself rather than in 3 dimensions. So we have P, F. I'm going to kind of show it like we did for in the definition of the dot product. Okay, so, and remember, this here, PF is parallel to the normal vector, right? This is going to be our angle theta. So I'm just going to call PT, I'm just going to call it W, just because it's a little bit easier in terms of labeling. So I'm going to let W equal vector PT. All right, so we want to find PF, that particular vector. PF, well, what is it? Remember, it's the projection of W onto N. Right, so N goes all the way here. Well, I can start here if you want, but we don't know how long N is. But W is the projection, EF is the projection of W onto N. Okay, so is projection of W oops, that didn't work. This. Okay, so let's remember a couple of things, right? So cosine in that triangle, cosine theta is adjacent over hypotenuse. Okay, we know that the dot product of W and N gives us the magnitude of each cosine of the angle in between them, theta. Okay, so that means if we solve for cosine here, no, this is good. This is taking a long time, but after this, then you can just, you don't have to show all this work. Okay. All right, so that means these are equal to each other. Okay. And so basically multiply through both sides by W, a magnitude of W, and they divide out. So here's how you can always get the distance between a point and a plane, okay, because if you have the equation of the plane, first of all, you have to find the normal to it. So if it's not in Cartesian form, you need to calculate what the normal is. And then remember, W is the vector from the point away from the plane to some point on the plane. So basically, from here, you're going to, first step, without showing all this work, first thing, find point on plane, find W, so that's vector from point away from plane to point from number 1, and then find the normal of the plane if you don't know it, and then use that, the dot product of those two vectors divided by the magnitude of the normal. Okay, so let's actually do it for this one. So, magnitude of PF. So what did we get? Did we find that vector yet? No, so we have our point. So PF, we need vector W. Okay, so that's going to be our new point when it's our original, or vice versa, it doesn't matter. So that's going to be 5, -5, -6. Dot product with the normal, which was 1, 2, -2. Okay, and then magnitudes of the magnitude of the normal. So 4 plus 4 is 8. So that's root of 9, which is 3. Okay, so then 5 minus 10 is -5 plus 12 is 7 over 3. And that's the same that we got using the first method. Okay, so that took a lot of work to get there, but you don't have to do all that work. If you remember this, then that's an easy way of calculating the distance between a point and a plane. Okay. All right, let's look at the next one. So it says find the acute angle between that line and the plane. Okay, so if you were, again, I'll do a little diagram here. There's my plane. Here's a line. And so we want an angle in between. So let's spin that so you can kind of see that. It says acute angle, because if we were, say, to look here, there'd be this angle, and then obviously compared to this side here, that would be an obtuse angle. So there's no sort of right or wrong. This is just asking you for the acute angle. So think about what you need here. You've got a line, so you have the direction vector, so that's good. Okay. And then you need, basically, to think about your plane. On a plane, you can get another vector, find 2 points, subtract them, get the vector, then you can do the dot product. But looking at this, if this is in Cartesian form, right away you know what the normal is. That's crooked, but you know that that's the normal. So what about if you find this angle in between them, okay? And then that forms a 90 degree with the plane. Subtract that from 90 to get the angle. Okay, now if it ended up going, the normal going down, then that would be more than 90. So we'll work through that, because I think this particular example will be that case. Okay, so let's get the direction vector of the line. So that's going to be 2, 4, 1. Okay, remember the denominator, that's like over 1. All of the x, y, and z terms are positive, so you know that there's no negative in the direction vector. Okay, our normal is 1, negative 1, 1. Okay, so let's find the angle in between them. So that's going to be 2, 4, 1, dot product 1, negative 1, 1 over 16, 20, 21, 3. Okay, so theta will be inverse cos of 2 minus 4 is negative 2 plus 1 is negative 1 over, you don't have to simplify, I'll show that as 63, so it's just one thing to enter in our calculator. So just make sure you're in degree mode. Second cos, negative 1. So you know, because the numerator is negative, you're going to get an obtuse angle here. Okay, so 97.2. Now it didn't say what to round to, so we'll go to 1 decimal place. All right, so think about what that looks like. Okay, so looking at this a little closer, I drew a different diagram, just so that it actually looks like 97.2. So this is my line here, and here's my normal going upwards. So the angle between them is 97.2. So obviously I use the direction vector going in this direction. This is where the plane is, this dotted line here. Okay, so looking at this, we could either take 97.2 and subtract 90, okay, to get the angle, that little angle in there. Okay, so you want the closest one, right? So therefore, angle equals 97.2 minus 90 equals 7.2. Or if you thought about this as, okay, well that angle is 97.2. I want the acute. That would be this angle over here, which would be 82.8. Okay, but still, that's not the angle between the line and the plane. It's the angle between the normal and the line. So to get this, we would then subtract 82.8 from that and get 7.2. Okay, so a couple of steps there. So you don't just want to subtract 97.2 from 180. That's not going to give you the angle between the plane and the line. It gives you the angle between the normal and the line. So remember, when we're using dot product here, we're using the normal vector. So we're finding the angle between the normal and the line. So it takes another step. Okay, so either you find the other angle and then subtract from 90, or you subtract 90 right away. Okay, and draw a little diagram if you can. You don't know, you don't have to scale it out. You don't know what direction, but just think about a line going through a plane. Planes here, and we're finding the angle in between them. There's a diagram that I've included. So we've got, it's like 2 pieces of paper that you've attached, or 2 pages in a book, that kind of thing. We want to know the angle in between them. So some angle properties back from previous math courses, perhaps back to junior high. What we do know from these planes, so plane 1, is that the normal here is 1, 2, negative 1, and plane 2 is 2, negative 5, negative 4. Okay, and we've labeled them there. So what can we do with this? We want to find the angle in between the planes, can we use the normal vectors? So they're drawn here. If I were to just do a two-dimensional, so of the edges, there's theta. So that normal, if I brought it out to the edge here, it's going up at 90 degrees. So maybe I'll go up this way. Oh, that's not very 90-ish. Okay, let's do that again. Go up there, that's 90 degrees. And then 90 degrees from this one, like that. Okay, well now we actually have a quadrilateral, right? So this now is quadrilateral, and we know it has to, angles add to 360. Well, we've already got 180 in here, so this angle in here has to be 180 minus theta to make a quadrilateral. Well, if that's 180 minus theta, then this is 180 minus 180 minus theta. Right? Because that's a straight edge. So when we simplify that, we get theta. Okay? So if we find the dot product, the angle between the two normals, I should say, then that's going to give us, so this part here, angle between the two normals, that's going to give us the angle between the two planes. So, ends up being pretty straightforward. Okay, so cosine theta is 1, 2, negative 1. That product with 2, negative 5, negative 4. Over magnitude 4, 5, 6, root 6. What's that? 25, 29, 35, 45. Okay, so theta equals cos inverse 2 minus 10 is negative 8, plus 4 is negative 4. Again, you know it's going to be greater than 90 because that's a negative value. Okay, so that's 104 again. I don't think I said what to round to. We'll go to the nearest tenth, so 104.1. Now, in this one, it doesn't say acute or obtuse because it doesn't really matter, right? So these planes keep on going forever, right? This way. And this keeps on going forever this way. So that angle or this angle doesn't really matter unless it's specified. If it's specified to be acute, then subtract from 180. If you did, say you changed the normal vector to go the opposite direction, then it would be 180 minus that. So you could, either of these angles is acceptable. Okay, so that's that.